Hello everyone, welcome for the first international workshop on security for Internet of Things, IOTS 2021. The workshop is held on May 16, 2021 in Duan for COVID-19. The workshop is organized in conjunction with EAI AC3 2021. The workshop was originally planned to be held in Xiamen, China. Just because of the COVID-19, the IOTS 2021 had to be held online totally. The workshop co-chair, Professor Zhiliang, Chen, and Lin would thank all the people behind the conference. There are many people efforts behind the conference held. Co-chair Zhiliang, Lin, and I would give many thanks to Dr. Guan from the University of Georgia, USA, Alexander, and all TPP members. Thank you for your amazing work, and I would thank all the authors to contribute their work to this conference. Without your help, the conference will not be held. And I still want to give thanks to EAI AC3 2021 Chair Erich Chen, Chen, Chenxin, Duan for their support to the workshop. Thank you.
Good morning, everybody. My name is Zhiyuan, and today I'll present a Thieves identification scheme for prepaid systems in smart grid. In this presentation, firstly, I'll introduce some concepts in smart grid, and then I'll analyze related work and its challenges. After that, I'll describe the proposed scheme and analyze its performance. Finally, I'll conclude my work. In conventional electricity grid, an operation center controls electricity generation, transmission, and distribution to meet consumers' consumption. With the development of public awareness of environmental conservation, more and more renewable energy come to use. However, the renewable energy sources are so volatile that the concept of smart grid has emerged with the idea of advanced metering infrastructure, aiming at improving demand-side management and energy efficiency, and constructing reliable grid protection against malicious sabotage and natural disasters. To achieve this concept, demand and response communication between the operation center and the consumers is expected in smart grids. Demand and response is briefly defined as the change in power consumption triggered by some utility actions in order to gain specific results. Therefore, it can be compared to a traffic light. For example, the green light is the feasible state. It means that the electricity grid operates normally and it's unnecessary to take any measure. Red light is the critical state. It means that the grid has been failure. It's impossible to take any measure to fix it. And the yellow light is the demand and response. There are some risks on the grid, but it's still possible to take measures to fix it. Demand and response needs high-frequency usage data from consumers. However, high-frequency usage data probably lead to consumers' privacy leakage. For example, from this figure, it can be seen that the consumer gets up at almost 8 o'clock and has lunch at 12 o'clock. If an insurance company gets the data, and for example, the consumer doesn't cook regularly or watches too much TV, maybe the consumer can't get a good contract. Therefore, it is necessary to introduce privacy-enhancing technology to smart grid. Before introducing our scheme, let's see some mathematical assumptions. Firstly is decisional determinant assumption. It means that it's impossible to distinguish t and another element x multiply mu. And the elliptic curve discrete logarithm assumption. It means it's impossible to get x from x multiply p. And the Q-strong determinant assumption. It means we can't get a pair from a tuple. Unfortunately, we expose our privacy information in our daily lives. For example, this is a figure from Daily Mirror newspaper in 2014. And from it can be seen that all G20 leaders' heights. For example, Haymaker is 5.5 foot and President Obama is 6.1 foot. Current privacy enhancing technologies can be categorized according to the information it will hide. For example, it can hide the subject's identity. Therefore, you can see that the first guy is 5.1 foot, but you don't know who it is. Or you can clock subjects' privacy information. For example, you can see that the first one is Haymaker, but you don't know how tall she is. For identity anonymity approaches, anonymous authentication is an important example. In traditional authentication schemes, senders' public keys are different. Therefore, from the public key, you can find the signature source. But in anonymous authentication schemes, all senders' public keys are the same. So you can only know that the signature is from a member of the group, but you can't find the real identity of the source. Different to traditional anonymous authentication schemes, key times anonymous authentication scheme is a conditionally anonymous authentication scheme. If a sender is honest and it uses all tokens only once, it can enjoy the anonymous. But if it sends a token twice, its anonymity can be revoked. One challenge facing electricity grid owner is how to charge for consumption. Payment mechanisms can be roughly categorized as postpaid and prepaid. The pay-in advance model has been proposed for prepaid schemes. The operating center sends a commitment to consumer who wants to join the smart grid system, and the consumer, after that, consumer can buy tokens from operating center, and each token is signed by the operating center using a blind signature. Therefore, the operating center can only see that the token is signed by itself, but the operating center can't find the source of the token. And when the consumer needs power, it simply sends the usage plan with its token to the operating center. However, the computational time and signal size increases as the number of tokens increases. But obviously, this model can achieve anonymity. Even the operating center can't see the source of the token and forger. Of course, the tokens are signed by the operating center. No one can produce a fake token to misinform the operating center. So it also achieves. It is also against Thieves. But in that scheme, malicious consumer who sends a token twice can't be found. Maybe a consumer resends the token many times to make the operating center failure. Therefore, it is necessary to achieve traceability. Traceability means that the operating center is able to track the consumer who sent the used token. Of course, in order to achieve traceability, the token should be from a consumer. A smart meter in the system, therefore it should achieve authentication, and the token shouldn't be modified. Therefore, it also should achieve integrity. Based on the analysis, here we improved the pay-in advance model, and in our model, the following security requirements should be achieved. Anonymity. Investigator can't obtain consumer usage profiles from a smart meter's usage reports. And authentication. The operating center ensures that the usage reports are from smart meters in the system. Traceability. Thieves can be identified if they try to send used tokens. And linkability. The operating center can't link different pseudonyms from a single source. Besides the security requirements, the scheme also should achieve energy efficiency. According to the discussion in the previous P-1 model, we can see that an important limitation of P-1 is the wastage. Of course, the operating center can set the denomination of each token to 1 cent, which would improve energy efficiency. However, this would lead to time-consuming computational costs during the power request time. Therefore, in the proposed scheme, no matter how much tokens are used, the computation time should be constant. The network model consists of a trusted third party, an operating center, and many smart meters. The number of smart meters is large enough for each smart meter to hide its privacy. Firstly, the trusted third party publishes its tokens, and after smart meter join the system, it buys tokens from the operating center, and during the power requesting time, smart meters plan their commitment and send them to the operating center with tokens. If the operating center finds a reused token, it reports the suspicious data to the trusted third party, which then calculates the identity of the malicious smart meter. In the P-advanced model, each token is independent. Therefore, a smart meter should send the corresponding amount of tokens to the operating center. But in our proposed scheme, we use virtual token. It means no matter how much electricity the consumer wants, it only sends the first token and the last token. Here is the scheme. Firstly, in the setup algorithm, trusted third party generates the token basis and publishes it, and the operating center generates its secret key and public key. If a smart meter wants to join the system, it computes a public key and sends the public key and its identity to the operating center. The operating center signs it as a commitment and replies the commitment to smart meter. The smart meter blinds the commitment and since the blinded commitment to the operating center. The operating center sends the blended commitment and replies it. The operating center using blind signature to send it. Therefore, the operating center doesn't know the blended commitment of smart meter. So, if the smart meter wants to use electricity, it sends the blended commitment and the certificate from the operating center and the zero knowledge proof to the operating center, of course with the first and the last tokens. The operating center validates the certificate is sent by the operating center using blind signature and the zero knowledge proof and of course tokens. If all of them are valid, the operating center replies corresponding amount of electricity. Otherwise, it rejects. If they are valid, but the operating center finds that a reused token, the operating center sends the suspicious data to the trusted third party, and the third party revoke anonymity of smart meter. The unlinkability of the scheme is based on the unlinkability of blind signature. Once tokens are used out, consumers must buy new tokens from the operating center and create new surnames and secret keys. The operating center can't determine whether two pseudonyms are from the same source. Anonymity of the scheme is based on the decision-not-defined assumption. It can be proven. Authentication of the scheme is based on the integrity of blind signatures. When the smart meter presents a signature during execution of the verification algorithm, it must prove that both the pseudonym and the secret key are authenticated by the operating center. If an attacker can frame a pseudonym, it means it can break the integrity of blind signature. Or if the attacker can produce a fake token, it breaks the ECDR assumption. And the traceability of the scheme is based on Q-strong defilement assumption. And this is an example. The power consumption is 960 watt-hour and the price of the power is 17.03 cents per kilowatt-hour. The four approaches are simulated in the same environment, and here is the results. From it can be seen The proposed scheme solves the token denomination challenge, and the computational time is reduced significantly compared to previous privacy-preserving scheme for prepaid mechanisms. And in this presentation, we describe a prepaid card system, and in the system, based on the system, we proposed a Thieves identification scheme. Based on the key anonymous authentication scheme, thieves can be identified. And we also proposed the concept of water token based on blind signature, and solve the token denomination challenge. And this is the references. This is the framework of the proposed scheme. And that's all. Thank you.
Hello everyone, today I want to introduce our paper that using smart contract to improve searchable symmetric encryption for you. A keyword index helps us search for documents connect a special keyword in a certain period of time. In order to search the crypto text, we can contract a special index, so we used a Bloom filter method for searchable system encryption. This figure showed a Bloom filter is what it always used to create index. Assume filter on U has encryption fields C1, C2, Cn on server S. The SSE scheme compares a function build index, search index, and 3 phases. In the setup phase, index for C1, C2, Cn are built by the search system. The retrieval test is performed in the search phase, and the update phase updates the index. When documents are changed, added, or deleted, the process of the setup phase is shown in the future. We use Bloom filter to construct searchable symmetric encryption scheme and use smart contract for fairness of searchable symmetric encryption scheme. We propose a no-interactive integrity verification scheme for search results for the first time. We use Merkle tree to verify the integrity of search results. In cryptography and computer science, the Merkle tree is a tree in which each leaf node is marked with the hash value of data block, and each leaf node is marked with the hash value of label of its child nodes. Assuming there are n documents, the keywords to be searched are represented by W. The file owner encrypts the keyword to trop.tw and publish the trop.tw and index collection I. The search then searches encrypted document according to trap.tw. The searcher calculates BF according to TW and the document's identity CID, and the search results are obtained based on BF. To ensure the integrity of search results, that is, the search has searched all documents rather than only some documents, and can be used on blockchains. We propose the scheme of the non-active integrity verification of search results. For the search results for the keywords in the document, we obtain the search results for each document. We then use each result as a leaf node to build a Merkle tree. We obtain the corresponding root node root when we finish constructing the Merkle tree. Here, search use their published key to sign the Merkle tree root node and obtain signs. Then we use hash function to generate a random number to construct the proof of results integrity. We compute hash sign and I to generate L random numbers, where L denote the security parameter. Assuming we have n documents that need to be searched, we created an array to save a proof of integrity of the search results, which we refer to as the array result integrity proof, which we called RIP. We then push the hash sign and I search result, that is hash sign I mod n, and its path in the Merkle tree into the array RIP. We also created a result array to save the search results. When the search completes the search, we output the result RIP and the sign root. The algorithm used to verify results and the integrity of the results is given in the following. When verifying the integrity of the search results, first we verify that the signature of Merkle tree roots. We then verified that the results in the array result are correct. Here, according to the root of the Merkle tree, we compute hash sign and I to generate L random numbers. Based on the generated random numbers and the document of compute search hash sign and I mod n. Then we verify that the price which would be provided in the array RIP of the Merkle tree of search hash sign and I mod n is correct. The algorithm used is verify result, and the integrity of result is given in the following. In the following, we discuss an example to illustrate the proposal scheme. Here, assume there are 4 documents that when the search is complete, we obtain 4 search results: search 0, search 1, search 2, and search 3. By using these 4 search results as a leaf node to build the Merkle tree, we obtain the corresponding root node. Assume Alice is searching for result. that Alice sends the root with her private key. The signs and I are joined together. We set I to 1 and 2. Thus we obtain two views. Sign join 1 and sign join 2. After hash and modulus, we obtain two random numbers between 0 and 3. Here, assume that hash sign join 1 is equal to 0, and hash sign join 2 is equal to 2. We save search 0 and search 2 and corresponding Merkle tree pass into the RIP area. The search 0 and the search 2 and the corresponding Merkle tree paths are used for subsequent result integrity verification. In addition, we assume that search 1 is result of the search cryptography. We save the search 1 in area result. If Bob is verified, Bob first verifies that root is area's sign. Then Bob verifies that the results in the area result are correct. Thus Bob verified that search 1 is correct. Then Bob, according to compute hash sign join 1 modded 4 and hash sign join 2 modded 4 to generate two random numbers. Here, Bob obtains two random numbers 0 and 2. Then Bob verifies the sign 0 and search 2 and the corresponding Merkle tree paths are correct, which complete the verification. Here we introduce the smart contract-based SSE scheme and provide a security proof. There are three rules in the proposed scheme: field owner, search, and miner. The field owner has a document denoted D1 and D2.dn. The search task is to search the corresponding document based on keyword and indexed provided by the field owner. The miner's task is to verify that the search results are correct and packet the transaction into the blockchain. The owner of the field first inputs the keyword to search and provide commission. When search found searching demanding, then the search searches the field according to the keyword and the index direction, and the search will submit search result and the result integrity provided to the miners. If the verification through, miner will package the results and the integrity proof into the blockchain. Our scheme has two phases. In phase 1, the field owner created a smart contract for search demand. In phase 2, for smart contract, the search can submit the results, and the miner can verify the results. The specific process is shown in the figure. The smart contract is in the following. A smart contract-based SSE is set of 6 polymer time algorithm SSE. Here we analyze the efficiency and the security of proposed scheme and compare it to related scheme. For users, search time determines the private and feasible of the SSE scheme. That's with pragmatic consensus calculation and communication costs during the search stage. Table 1 shows how the proposal scheme performs in the search phase compared to related scheme. As shown in table, the search time of the scheme proposed camera is the fastest because the scheme is designed to run parallel. However, this scheme do not safety fairness, do not provide an integrity proof of the result. That if search return incorrect result, or if the search disappeared after receiving the commission from the user will lose both money and the search results. Therein lies the unfitness. To achieve fairness, another scheme requires the least 6 transactions and 3 combinations, which may prolong the time required for user to obtain results. The proposed scheme only requires the 2 transactions and 2 round communication. Here we conduce the relevant experiments on the number of different fields and the numbers of keywords, and we compare the time of completeness of the generated result and the search time. The experiment data are shown in the table. From the experiment data, we conclude that after adding the result integrate verification, the overall time is double, which is still within the acceptable range. Thus, we consider that the proposal system is available. Thank you.
Hi everyone, today I want to present this paper, a novel approach for code smells detection based on deep learning. This paper is co-authored by Tao, Fu, Xue, and Luqun, and I am Tao Lin. This paper was published by EAI International Conference on Applied Cryptography in Computer and Communications. Compared to software bugs, code smells are more significant in software engineering research. It is not easy to detect code smells through traditional methods. In this work, we propose a novel code smell detection approach based on deep learning. The experiments show that our work achieves high scores in terms of F2 score and kappa values. Code smells are increasingly generated by modern agile software development. This is because code changes are much more frequent and occur on a daily basis for large software companies and dominant open source communities. Although there are many more tight approaches to detect code smells, these methods have some defects. Due to the frequent changes, it is increasingly probable to generate code smells or overheads. Code smells, like software bugs, are a serious problem in modern software. Nowadays, the code smells are being researched by many practitioners. software developers are not aware of what is the code smell, although they are aware of software bugs. Thanks to Integrated Environment Development Kit (IDE) that can provide many instant suggestions and notifications when there are bugs. The question here is how to detect code smells effectively, and what is the motivation for detecting code smells. Although there are many more tested approaches to detect code smells, these methods have some defects. We leverage deep learning on code smell detections. There are mainly two categories of deep learning networks. One is recurrent neural networks, and another is convolutional networks. Convolutional networks have already demonstrated its usage by leveraging hierarchy features. In this paper, we use fully convolutional networks for code smell detection based on semantic features. We will define the type of neural network we use and explain how it is used to detect code smells. An advantage of using convolutional network is its ability to identify and use local correspondences. In recognition and machine learning, convolutional networks are increasingly significant. Convolutional network presents the improvements on image recognition. An example is using convolutional network on local correspondence. In software engineering, we definitely can use this kind of information for code smell detection. To our knowledge, this is the first work to train a convolutional network for code smell recognition. The inference is much more improved through convolutional network. Unlike previous work that needs additional information for code smell detection, this work does not use any existing information for code smell detection. One of the major challenges in code smell detection is to find relationship between code semantics and code location. There is a trade-off between identifying the correct semantics compared to identifying the correct location of the smells. Although there are several success stories from image recognition by using deep networks, it is hard to transfer these approaches to software engineering, which is more deterministic. Fully convolutional network has been used for one-layer computation and has the potential to deploy to multi-layered environments. We can define a multi-dimensional array to represent the convolutional network, h times w times d, where h and w are space dimensions, and d is the channel. The first layer is our source code input. The second layer is the network for sequence modeling. For example, the inputs are x0, x1, x2, x3, x4 until xn, and the outputs are y0, y1, y2, y3, y4 until yn. The final output will be reshaped to one-dimensional array, where size will be d times 1024. This output array will be dilation blocks. For the encoder task, we should process noise. Each layer in the encoder is processed by normalization and linear analysis. With recent development in software engineering, It is easy to find software bugs using several methods from compiling to running. Our work is based on the state-of-the-art deep learning method for detection and recognition tasks. Firstly, we transform the software source code to XML file in order to be processed by deep learning models. Then, there are two steps: code segment proposal and classification. The code segment proposal leverages the heuristic search to generate following inputs. These segments are processed by CNN classifier. We try to use RCN, otherwise, one of the main reasons is that RCN uses selective search algorithm, which is time-consuming. We use the following equation for segments. In this equation, seg is the segments, R is the rule of limits, and P is the process variable. Q is the next graph input, I is the interception, and D is the next destination. We use an open source database published by the author's previous work. The experiment results are shown on the following table. And we try to detect this kind of code smell categories: long method, lazy class, speculative generality, refused bequest, duplicated code, contrived complexity, shotgun surgery, and uncontrolled side effects. From this table, this work achieves high performance in terms of F2 score and kappa value, especially for the category of uncontrolled side effects and contrived complexity. In this work, we conducted a research for code smell detection based on deep learning. Our solution uses convolutional neural network for training a model to detect several common code smells problems in software engineering. The solution achieves satisfied F2 score with average above 0.75 and also achieved a satisfied kappa value with average above 0.8. And part of this work is from previous PhD research at the Pennsylvania State University before I joined Amazon. And thank you.
Hello everyone, I am glad to be here to present our paper entitled Towards the Adaptability of Traffic-Based IoT Security Management Systems to the Device Behavior Illusions. In this paper, we give a brief but systematic discussion about the performance of existing IoT security management systems in non-terms when faced with the device behavior illusions. Firstly, let's start with the background. Recent years have seen the rapid development of Internet of Things technology, with different kinds of IoT devices widely deployed in various scenarios, such as smart home, smart city, and industrial control. IoT traffic is now a major contributor to the overall Internet traffic. It is expected that IoT traffic will account for more than half of the Internet traffic in 2022. However, the proliferation of IoT devices brings not only convenience but also security threats. Due to constrained computation and communication capacities, IoT devices have become a new focus of malicious attackers. For example, Mira is a large-scale botnet which is mainly composed of compromised IoT devices. It has caused great damage by launching powerful distributed denial-of-service attacks. It is also demonstrated that such IoT-based botnets are becoming more and more resilient and can even bring down the power grid. Given the severe security threats brought by IoT devices, customized security management systems are in high demand. Considering IoT devices usually have only very simple functionalities, and as a result, their communication traffic can be well characterized. Therefore, a lot of traffic-based IoT security management systems have been developed to enhance the security of networks equipped with IoT devices. We focus on 3 different classes of traffic-based IoT security management systems in our work. Firstly, the timely identification of what type of devices are connecting to the network is usually the first step to enable further customized management policies. And device identification systems can also help with the discovery of unauthorized or vulnerable devices. Secondly, it is presented that the events happening on IoT devices that trigger the changes of their working statuses, also known as trigger events, often correspond to some fixed traffic patterns, based on which event fingerprinting systems are developed. With the persistent awareness of the working statuses of all the devices, network managers can monitor the statuses of deployed IoT devices and ensure that they function normally. Thirdly, intrusion or anomaly detection systems aim to detect all kinds of attack traffic sent by malicious attackers to compromise IoT devices, as well as the misbehaviors by IoT devices themselves. Based on the simple functionalities of IoT devices, anomaly-based intrusion detection systems, which build the profile of the normal traffic generated by IoT devices and regard any traffic deviated from the profile as intrusions, become popular in the networks serving IoT devices. But how do existing works develop and evaluate their proposed systems? Usually, it is impractical to collect traffic traces spanning long time periods for the training and test of these IoT security management systems for prototype verifications in laboratory environments. And the similar often goes the same for real-world environments. Therefore, for the evaluations of these IoT security management systems, both of the training and test processes are based on the traffic datasets collected in short time periods. Nevertheless, when we take into consideration the special application scenarios of IoT devices, the long-term performance of these systems should be critical and tends to be questionable. Many IoT devices interact with changing environments. The changes of weather or seasons will also influence the user activities and then change the way they use IoT devices. Moreover, technical issues like software or firmware updates and configurable properties may also make the traffic profiles of IoT devices change dramatically. Thus, a problem of adaptability, whether existing IoT security management systems can keep their high performance in the long-term running, arises because the characteristics of traffic generated by the same IoT devices may keep evolving in the process of usage. Adaptability is of great importance for practical IoT security management systems to be deployed in real-world scenarios, without which the systems will be very fragile and the behavior evolutions of IoT devices can easily jeopardize their performance and then compromise the network management. To tackle the problem, the following open research questions remain to be investigated. First, how device behavior evolutions caused by different factors will affect the traffic profiles of IoT devices. Second, can current IoT security management systems based on the traffic profiles adapt well to the device behavior evolutions? Third, what are the possible solutions to improve the adaptability of IoT security management systems or build self-adaptive systems? To serve as the base for further studies on the building of adaptive systems for the security of IoT devices, in our paper, we try to review the previous works and envision the possible solutions. At first, we give a taxonomy for the possible behavior evolutions on IoT devices. Then, we summarize the popular traffic characteristics used in existing IoT security management systems and their adaptability to different kinds of device behavior evolutions. Finally, we envision possible solutions to tackle the adaptability problem. Machine learning methods are widely used in existing IoT security management systems. A similar problem to react to change, called concept drift, has already been investigated in machine learning community. In predictive analytics and machine learning, the concept drift means that the statistical properties of the target variable, which the model is trying to predict, change over time in unforeseen ways. This causes problems because the predictions become less accurate as time passes. In the following context, we use the term concept drift and IoT device behavior illusions interchangeably. IoT device behavior illusions can be simply divided into three classes. At first, the software or firmware updates can bring functional changes to the traffic generated by IoT devices. While due to the constraint of device hardware, this kind of updates are not frequent, usually monthly or even more infrequent. However, for IoT devices, the delivery of update notification cannot be foreseen and usually brings functional changes. It is a kind of sudden or abrupt drop. Secondly, many IoT devices support configurable parameters, either technical, like content delivery networks, or user-oriented, like trigger action rules and user credentials. Usually, this kind of drifts will not affect the functional patterns of IoT devices, but only change the length of a few packets in the flows. For example, the length of DNS response packets and the server IP addresses can vary in a small range due to the content delivery networks. Similar are the packets that contain the user set credentials and server certificates. Finally, since the application scenarios of many IoT devices are tightly relevant to the human's living and production activities, the changes on user habits and the environments, like weather, season, and temperature, can also influence the device behaviors by changing the ways how users use the devices. This kind of drifts are mainly manifested in the statistical characteristics of the traffic generated by IoT devices, because they originate from the changes on the durations and frequencies of the use. For example, surveillance cameras are silent when users are at home and generate much large volume traffic when the users leave their houses. The using frequency of air conditioners can vary a lot in different seasons, due to the non-short periodicities of the Earth's environments. This kind of drifts can be incremental and gradual in short terms, but recurring in long terms. Then, let's see the popular traffic features used in existing traffic-based IoT security management systems. For device identification systems, some works utilize identifiable fields in the traffic to recognize IoT devices, such as destination IP addresses, domain name queries, and certificates. Others leverage features in different resolutions, including packet level, flow level, and session level, with machine learning models to classify traffic generated by different IoT devices. Many device identification methods extract feature vectors in terms of traffic traces collected in short durations, ranging from minutes to hours. Both of the selected features and the durations of instances to be classified may influence the adaptability of the device identification methods. What's more, in the evaluation of these works, the training and test datasets are usually derived from traffic generated by the same devices in different periods, completely ignoring the impact of the deployment environment and user habits, which may matter much to the real-world scenarios, especially in long terms. Unlike device identification, event fingerprinting systems tend to use very simple features, like short sequences of packet lengths and directions, to detect the events happening on IoT devices by pattern matching. Intuitively, although such simple signatures can be very precise, they are also very fragile at the same time, because the most minor update of the firmware or changes on distinct device configuration parameters, like credentials and device IDs, could destroy the signatures, and it will take much effort to maintain the signatures if the changes are frequent. As for intrusion detection systems, some works perform high-level policy verification based on the event-level signatures, while others follow a similar paradigm to extract statistical traffic features and use machine learning models to detect intrusions. Given the popularity of anomaly-based intrusion detection systems, without taking into consideration the factors which may make the communication behaviors of IoT devices deviate from the known normal profiles by themselves, the long-term performance of these intrusion detection systems for IoT devices may be quite questionable. Having said the behavior illusions of IoT devices, there may also exist some stable traffic features, like protocols and ports used by the devices, because the hardware and the core functionalities of IoT devices can hardly change after coming into use. However, intuitively, these relatively stable features are not distinguishable enough to achieve the goals of IoT security management. Thus, the adaptability of IoT security management systems to the device behavior evolutions should get more attention. Both of the empirical evaluations and the enhancement of the adaptability of IoT security management systems are in high demand in future work. So, what are the possible solutions to cope with the IoT device behavior evolutions? A preliminary method is to enrich the training datasets so that the datasets can cover all the possible traffic patterns that IoT devices may exhibit as much as possible. However, on one hand, this increases the overhead to prepare the data and makes the performance of systems sensitive to the training datasets. On the other hand, this method may only apply to the evolutions caused by user activities, and the changes incurred by device software or firmware updates are usually unpredictable and remain unsolved. What's more, for anomaly detection systems, current user habits are also important factors to determine whether the ongoing device behavior is abnormal or not. It may hinder the system performance to simply add the training data without proper context. Another possible solution is to enable lifelong learning and detection for the systems, which is a hot topic in current anomaly detection community. Lifelong learning means that when the system makes some mistakes, it can be trained incrementally by directly learning from the administrator's feedback to avoid making the same mistakes again. This method is a kind of remedy afterwards with lots of human intervention and cannot eliminate the performance loss caused by evolutions proactively. Additionally, it is also challenging to make the system get aware of the different contexts between the newly coming feedback and the previously learned model that should perhaps be forgotten sometimes. Finally, adaptive learning methods in machine learning community that update predictive models online during their operation to react to concept drifts may provide inspirations to deal with the IoT device behavior evolutions. However, a lot of future work is still needed to dive deep into the regularities of IoT device behavior evolutions and combine general adaptive learning algorithms with the IoT security management objectives. To summarize, in this paper, we focus on the adaptability of IoT security management systems to the device behavior evolutions. We give systematic summary and analysis on the existing IoT security management systems, different kinds of evolution happening on IoT devices, and the possible solutions to build adaptive systems for the security of IoT devices. We find that the adaptability of IoT security management systems didn't get enough attention despite its great importance. Future research efforts may contribute to this problem by the following ways. Firstly, perform thorough measurement and characterizing to the concept drift in IoT traffic. Secondly, provide open datasets collected in non-time periods consisting of all kinds of device behavior evolutions to help researchers better evaluate and improve their systems. Finally, solutions like adaptive learning algorithms specially designed for the IoT ecosystems are in high demand. Our team has been working on a systematic solution, and the study is hopefully to be appeared soon. We also hope our work can serve as the base for further study on adaptive IoT security management systems. That's all about our paper. Thanks for your listening, and questions are welcomed.
Hello from the EAI team. We have a great new feature in the EAI Compass that you can use. Upvote your favorite presentations to show appreciation and respect to the best presenters. Open up the EAI Compass, go to the program, find the presentation you want to upvote, and hit the thumbs up button. It's that simple.
It's my honor to announce the close of the workshop, and we look forward to the next year. Thanks for all the people involved in this workshop. We really thanks to all the authors who submitted paper to the workshop, and thanks to all the presenters of their amazing talks. And we really appreciate the help from the AC3's organizer and thanks to the EAI for the sponsorship of the IOTS. And I really want to thank again for all the people involved. Thank you. We look forward to next year, 2022.